So, let us look at the heat transfer in developing flow, that is what our main aim was. Okay. So, heat transfer in developing flow, we would come to the point that where you basically are dealing with a situation that in the entrance region, how does the heat transfer happen. So far we have dealt with the fully developed limit. We have established how the temperature varies, fully developed temperature profile varies as a function of R only, right, that we established. Okay. That means a normalized temperature profile. We also saw that what is a hydrodynamically fully developed region, how does it look like. But let us now look at the thermally developing part, so that we can get an idea that how that is going to vary. Okay. So, there are situations, can be two situations. This is very similar to what we saw in our flat plate boundary layer, that how the two boundary layers are actually developing. This is delta T. So, this is once again x, this is once again x T, right. So, in this particular case, your delta T is less than your delta, corresponds to Prandtl number much greater than 1 slot. This is like delta T is greater than delta, okay, and Prandtl number is therefore much less than 1. These are the two limits that we are very familiar with, right. And we already know that what Prandtl number greater than 1 means. Okay, that means of course that your thermal diffusivity is larger, right. Okay. So, that is how you are going to carry this. Okay. So, greater than 1, less than 1. Okay. So, let us take the limit of Prandtl number much less than 1, okay, which means that the delta T is actually greater than delta. Okay. So, this is the condition. Note that the definition of Prandtl number is gamma by alpha, right. So, when we say that this is much less than 1, this essentially means that alpha is much greater than gamma, right. So, in essentially what it means is the thermal diffusivity is more than the momentum diffusivity. So, in this case, by the definition of Prandtl number, this is what we have. So, delta T is much greater than delta. Okay. So, like your flat plate, okay, like your flat plate, delta T is proportional to x, Prandtl number to the power of minus half, Reynolds number x to the power of minus half. Okay. So, that is from the flat plate analogy that we already did, okay, for delta T which is greater than delta. Do you remember? So, you can just flip your notes and you can go to that particular page. So, at the end of developing length, at the end of the developing length, you have delta T proportional to x T, Prandtl number to the power of minus half, Reynolds number x T to the power of minus half, right. Okay. So, at the end of the developing length, so that is what x T is at the end of that particular segment, right. Now, delta T is obviously at that particular point is nothing but the hydraulic diameter, right, of the duct, right. So, this is the hydraulic diameter. Okay, as the hydraulic diameter. Therefore, we get dH is proportional to x T, Prandtl number to the power of minus half, Reynolds number x T to the power of minus half, right. Okay. Or in other words, dH is proportional to x T. Remember, this Reynolds number is cast in the terms of the length scale, which is x, not with respect to d. Okay. Or in other words, dH by x T, Prandtl number to the power of half into u x T by u x t by gamma is of the order 1, right, should be of the order 1, roughly scales as 1, right, or in other words, if you now convert this particular Reynolds number to the corresponding diameter, I mean use that as the relevant length scale. So, x t by d h into 1 over Prandtl number write it properly, Prandtl number, Reynolds number d, right, to the power of half is proportional to 1, right. So, that is what you have over here. Okay. So, for this situation, so that is, this is very important because we will use this length scale very shortly. Okay. In how we will use it, we will see. Okay. Now, okay. If you now also look at this thing in a little bit more detail, this is the generic expression once again. So, x by delta t into Prandtl number to the power of minus half, Reynolds number x to the power of half is proportional to 1, or x by dh, dh by delta t, Prandtl number to the power of minus half, Reynolds number x to the power of minus half, this entire thing scales as 1, or x by dh to 1 over Prandtl number, Reynolds number dh to the power of half, dh by delta t is proportional to 1. Okay. So, as dt approaches dh, this particular ratio approaches 1. Okay. So, this particular ratio approaches, in the limiting case it is 1, as this approaches your dh, right. So, basically x by dh into 1 over Prandtl number re dh, okay, to the power of half, okay, is equal to 1. This is the one that governs, right, transition from developing to fully developed, right. This is the transition, this is the number, right. As it approaches 1, the flow becomes more and more fully developed. So, that is what we have got. Otherwise, normally your dh will be more than your delta t, right. So, this particular number, okay, has to be less than, if this is much greater than 1, this has to be less than 1 for the ratio to be equal to 1, right. So, therefore, as this approaches 1, okay, the flow becomes more and more fully developed. So, you are going to the fully developed regime, which is based on this particular criteria, right. So, that is an important part that one should understand, right. Next, we look at the case of Prandtl number greater than 1, right. We did it for Prandtl number less than 1. Okay. Now, here one important thing that we might want to do, if you recall your flat plate boundary layer, we did a scaling. Remember that we did something like this to establish the velocity scale. This is what we did, okay, for u, for scale of u. Okay. However, the basic assumption in that particular case was that delta t is much greater than or delta is much greater than delta t, right. That was the assumption in a flat plate boundary layer. Okay. So, therefore, this scaling was valid, but here it basically spreads over the whole diameter of the pipe. So, therefore, this scaling is not correct over here. The scale of u is still capital U, okay, that is still the scale, okay, because there is no there was no imposed scale, right. So, and the layer of delta t was much thinner compared to the delta. So, therefore, you could get away with this kind of a scaling. Now, so therefore, in this particular case also you apply the same thing, which makes it x by dh right. So that is what you this is what you got earlier, okay, from your hydrodynamics. Okay, this is from the flat plate. Instead of writing or, let's put also, okay, over here. So therefore x by xt is 1 over Prandtl number, or xt by x is equal to Prandtl number for all Prandtl number now, right, because your scale has not changed, so there is no difference. Okay, got it. So therefore for x less than xt, Nusselt number is given by d k q double prime into delta k into dh by k that is the Nusselt number value, right. So in this developing region, got it. So remember two things, one is that this is that for all Prandtl number, this is different from a flat plate where we had that Prandtl number 1/3 and half kind of a discrepancy, right. Here actually that does not exist, and also the Nusselt number definition is given by this. Okay. So these two are two important points that you should always remember. Okay. Now this sets the stage now to do a detailed analysis of the thermally developing flow, which is basically the Poiseuille flow. So we would take that the hydrodynamics is fully developed, that means the flow is hydrodynamically fully developed, but it is still thermally developing, right. Okay. So that is the case that we are going to take over here. So thermally developing but hydrodynamically fully developed. Okay. So as you can see, the first thing is your x lies in between these two limits, that means x is greater than the hydrodynamic entrance length, right, but it is lower than xt, which is the thermal boundary length. Peckley number is much greater than 1, and Prandtl number is much greater than 1, right. So these are the two, these are the things that we have kind of put over here. T naught, which is the wall temperature, is equal to constant, and of course you have dt by dr is equal to 0, still at r equal to 0 because of the symmetry, and we put a temperature T in, which is basically the inlet temperature for x greater less than xh. Okay. Okay. So you can fix the origin whatever. Okay. So you can fix the origin at x equal to xh. In that case, this will be less than 0. Okay. So it depends on where you are fixing the whole thing, right. So this looks like this. Okay. So basically your hydrodynamic boundary layer has fully developed here. Is delta. So this is your basically your coordinate, this is your region of interest, so to say, and this is T naught is equal to constant. Okay. So this is your T naught equal to constant, this part, okay, and this is your hydrodynamically fully developed regime. Got it. So based on this, okay, let us start defining. Define G, okay, is equal to T minus T naught divided by T in minus T naught, right. T in is the inlet temperature, right. R bar is equal to R by R naught. This you are already familiar with. For X bar, that is for non-dimensional if we have to non-dimensionalize x, then it is x by d divided by RED into Prandtl number. Remember, this scaling now becomes important, which we established just a few minutes ago, right. So, this comes essentially from your scaling argument, and this scaling argument evolved very naturally, right, because we know that when this was equal to 1, we got to the hydrodynamically fully developed to the thermally fully developed regime, right. That was what we actually did, right. So, if we recall all the assumptions that we had over here, what does the assumptions actually say? That first and foremost you are within. So, if this is basically your xt somewhere there. So, we are only interested in this intermediate region, because beyond this we have already done our analysis, okay, for constant wall temperature and constant heat flux, right. So, here we are taking the case of wall temperature is still constant. So, it is, we are not varying that. The profile of temperature, by intuition you can say that it actually should have an inflection point at r equal to 0, that is at the center line, and the inlet temperature is taken to be the inlet, okay, whatever is the inlet temperature, okay, but we are considering our axis starts basically from your x equal to h, right. So, the inlet temperature actually is x less than 0 to say. And there are 3 parameters we are defining. One is G, which is basically nothing but a non-dimensional temperature. It is different from how we defined it earlier. Now, you have a T in coming into the picture. Previously, we did not have that. Then of course, you have the R bar, and this particular term is very important, which one could only establish through the scaling argument that we did earlier. So, this is just a brief recap or a brief emphasis on what needs to be done to approach the problem. So, next is the energy equation, obviously. Okay. So, energy equation right, that is the full fledged energy equation. Of course, you still have the Peckley number much greater than 1 limit. Okay. So, u is basically 2u into 1 minus r bar square, T equal to T naught plus G, T in minus T naught, R is equal to R naught into R bar, X is basically equal to D RED Prandtl number X bar, right. So, these are the parameters which we are going to substitute now in the expression and try to see what does the math, how does the math actually evolve, right. Okay, so, let us take term by term, that is easier for us to do, because that would give us that flexibility, and then we can assemble all the terms together. So, dt by dx is equal to dg by dx T in minus T naught, which is basically equal to dg by dx bar T in minus T naught divided by d Reynolds number d into Prandtl number, right. So, we have just used the scale for x in this particular expression. So, then you of course is dt by dr, and that is given as dg by dr T in minus T naught dg by dr bar T in minus T naught into 1 by r naught. Okay. So, that is the second term that you get. Similarly, dt square by dr square. So, we are writing term by term, as we said, 1 by r naught square T in minus T naught d square g by d r bar square, right. That is what we have done. So, these are the 3 terms. Now, the basic task is to basically assemble all these terms together, so that we can get a nice expression. So, 2u 1 minus r bar square by alpha T n minus T naught by d into RED into Prandtl number and dg by dx bar, right. That is the first term. 1 over r naught square T in minus T naught d square g by d r bar square plus 1 over r naught square 1 over r bar T in minus T naught dg by dr bar, right. This is the full fledged expression assembling all the terms. So, this is basically assembling all terms, right. Okay. So, therefore, moving on, or so a little bit more mathematical manipulations. Okay. Or in other words, half plus 1 by r bar dg by dr bar, right. So, that is the final form of the expression that you have. Okay. As you can see, there are two variables, almost impossible to solve because g is no longer a function of only r. Okay. It is a function of both x and r, right. So, the boundary conditions are g equal to 0 at r bar equal to 1, which is given, right. dg by dr bar is equal to 0 at r bar equal to 0, this is symmetry, okay, and g is equal to 1 at x bar is equal to 0, right, because that is the point where we have the same temperature, the temperature is the same as the inlet temperature, right. So, based on these expressions, so to say, okay, we move forward, got it. Okay. So, this equation actually presents, it can be only solved, we will try to solve it analytically. So, there are methodologies by which you can actually solve it analytically. So, one of those methodologies will be the separation of variable or SOV. Okay. So, separation of variables, you can read up a little bit on separation of variables in your math from your math book. Okay. So, separation of variables is something that you have encountered quite a bit in your conduction courses, because many of the conduction equations actually has that kind of a thing. Okay. Now, if you look at the nature of this equation once, so you can see one thing very prominently. Okay. If you just look at this term, okay, I mean this term and these two are basically the same. So, these two terms, right. You can see that it is now a function of two variables, where your x bar kind of is like a time, okay, whereas r is more like the spatial distance. Okay. So, so we will see while we are doing this. Okay. So, what is our expectation? Our expectation is that the temperature would show a certain amount of behavior, certain kind of behavior with x bar, right, because as x bar increases, okay, something is going to happen to the temperature profile, right, that is what is expected is going to happen. Now, what is the general expectation? See, when we actually propose that what is going to be your g, let us write the g here one more time so that you guys get an idea, T by T naught into T in minus T naught. So, what happens to g as we go on increasing x bar? Does g skyrocket or it does not, right? So, obviously, t is something that is bounded, okay, it cannot go beyond a certain value, it cannot go beyond t naught, right. So, based on that, okay, whatever is the solution that we will get out of solving this equation has to be physically meaningful also. That means you cannot have a temperature profile which skyrockets, which increases all the time. Similarly, you cannot have a temperature profile which cannot have a temperature profile which shows an unphysical nature, right, even if it is mathematically correct, right. So, based on some of those limitations that we have, we are going to do the separation of variable, keeping in mind that this is our main variable, which is g, which is a function of both r and x, right. So, separation of variables we are going to attempt in the next class, and we are going to see that how this separation of variable actually works and what it actually leads to, what are the expressions that we get ultimately out of it. Thank you.